is Mama Afi bin Momano. I am from Group 1.
Hi, my name is Nurul Najha Masri. I am from Group 1.
Okay, hi, I'm Aisyah Lazura binti Muhammad Tamizi. I'm from Group 1.
My name is Ali. I'm from Group 1.
Hello guys, this is Islam Mazharul and I am from Group 1. Today we will talk about the chapters which is orthogonality. We will see the definition of orthogonality, the properties of orthogonality, characteristics, and we will see later on the some theorem of orthogonality. So let's move the first things. The first topic is the definition. So what is orthogonality? We will see here. The definition of orthogonality is we say that two vectors are orthogonal if they are perpendicular to each other. The dot products of them will be 0. So what is perpendicular? So we assume two vector. We assume two vector here. Vector A, vector B. So perpendicular means vector A and vector B, in between of them there is an angle. The angle will be 90 degree. So this is the meaning of perpendicular. The second definition, if we look here, is two vectors U and V in Rn are called orthogonality if U dot V is 0, equal to 0. Meaning here that their dot products will be 0. The relation of orthogonality in an inner product space is symmetric. Symmetric means if I give you an example, will be clear. That is, let's see, alpha is orthogonal to beta. So we can write here alpha beta equal to 0. So when we will talk about symmetric, there will be a bar on top, and when we will remove the bar here, so alpha will they will change the place. They will change their place. Beta, alpha. So meaning here that if alpha is orthogonal to beta, beta also orthogonal to alpha. The next one is if non-zero vectors R1, R2, Rk are mutually orthogonal, they are linearly independent. Properties of orthogonality. So we will see here the properties of orthogonality. Number one, prep B is a subspace of Rh. So number two is the only vector that lies in both V and prep B is 0 vectors. So the only vector will lies in vector V and vector prep V is a 0 vector. So prep V prep is equal to V. Then number 4 is the 0 vector is orthogonal to every vector, meaning here that whatever we will multiply with 0 vector, let's see, if we multiply 1 will be also 0, meaning whatever we will multiply with 0 vector, the result will be 0.
Hello guys, today I want to explain theorem of orthogonal matrices. And first one, the columns of n m times n matrix Q from n orthogonal set if and only if transpose Q times Q equal to in. And from the previous theorem, it is clear that n times n matrix Q whose column form an orthogonal set is called an orthogonal matrix. And next one, a subspace matrix Q is orthogonal if and only if Q inverse -1 equal to transpose Q. And example, the stand matrices of rotation are on signal Y for A equal to constant negative sin theta and sin theta negative cos theta. And next one, let W be a subspace of Rn, then proof W is a subspace of Rn, and proof W equal to W, and W summation proof W equal to 0. D is last one. If W equal to span W1 until Wk, then V is in proof W. If and only if V times W1 equal to 0 for all I equal to 1 until K. For the subspace associated with an orthogonal matrix, we have the following results.
Okay, now we will talk about some theorems of orthogonality. So let's look. The first theorem is let V1, V2, be an orthogonal basis for a subspace W of R to the power n, and let W be an vector in W. The unique scalar in the expansion of W equal to C1 V1 plus C2 V2 plus CR VR. So are given by Ci W dot vi for I equal to where I equal to 1 2 3 until k. Okay. Theorem 2 is let Q1 Q2 until Qk be an orthogonal basis for a subspace of W of Rn. So then any vector of small w of W has the unique expansion where W equal to W minus Q1 into Q, W plus W into Q1 into Q2 plus W until Qk. This flow will go until Qk. Theorem 3 will be if W is a subspace of Rn, then dimension plate W equal to n. Theorem orthogonal decomposition, let W be a subspace of Rn and let V be only vector in Rn. Then there are unique vectors where small w in W and prep small w and in prep capital W such that V equal to W plus prep W.
Hello guys, and then we talk about characteristic. And first one is inverse matrix is also orthogonal. It means if A is a orthogonal matrix, so we want to do the inverse A matrix. It means inverse matrix, the inverse A also is a orthogonal matrix. And 2, product is also orthogonal. And just follow this. And 3, the determinant has a value of positive or negative 1. This means the determinant of orthogonal matrix have a value of the positive or negative one. And for the two vectors u and v in Rn are called orthogonal if u dot v equal to 0. And 5. The relation of orthogonality in an inner product space is symmetric.
Hello guys, okay, today I'm going to show you some of questions on orthogonal. So in this particular case, you want to find whether this vector A and vector B is orthogonal or not. So vector A, which is 4, 2 and 1, while vector B is 1, -3, 2. To find orthogonal, to find whether this vector orthogonal, this vector product must be equals to 0. Alright. Okay. Vector A dot vector B. How are we going to solve this problem? So component, the first component, A1 times B1 plus the second component, A2 times B2 plus the third component, A3 times B3. Okay, let's solve it. Alright, A1 4 times B1 1 plus A2 2 B2 -3 plus A3 1 and B3 is equal to 2. So we are going to get 4 plus -6 plus 2. This is equal to 0. So in this particular case, vector A times vector B, we get 0 as the answer. So this means that vector A and vector B is orthogonal. Alright.
Now we proceed with the second example, which is called as orthogonal subspace. So for the orthogonal subspace, the rule is just simple. So first we must have every vector of subspace A is orthogonal for every vector of subspace B. For the second condition, the vector A is the element of subspace A and the vector B is the element of vector B. So the subspace of A is made up of vectors from 2, 0, 4 and the subspace B is made up of vectors from 0, 3, 0. So how to solve this question? By using the dot product. So by using the dot product, we must calculate A1 times with B1 plus A2 times with B2 plus A3 times with B3. So we substitute the value. So A1 is equal to 2 and B1 is equal to 0 plus A2 is equal to 0, B2 is equal to 3, A3 is equal to 4, B3 is equal to 0. So we calculate the value. 2 times 0 is equal to 0 plus 0 times 3 equal to 0 plus 4 times 0 is equal to 0, which is the answer is equal to 0. Hence, subspace A and subspace B is orthogonal.
Hi. So next we're going to check on orthogonality metric by using this theorem. A times A transpose is equal to identity. This is the example. Example of matrix A, I'm using cos x, sin x, negative sin x, cos x. First of all, we need to find the transpose of A. So the A transpose is okay. Next, we have to A times 2 A transpose. A times A transpose. So we copy the A matrix, which is cos x, sin x, negative sin x, cos x. For the A transpose, we have cos x, negative sin x, sin x, cos x. So, next, the answer for the multiplication of A times A transpose is, we have cos square x plus sin square x negative sin x cos x plus cos x sin x negative cos x sin x plus sin x cos x sin square x plus cos square x. As we know, cos square x times cos square x plus sin square x is equal to 1. Negative cos x sin x plus sin x cos x is equal to 0. Negative sin